Hello, this is Mr. Huff. Before you watch this video, make sure you have watched this general discussion video about the Reynolds number to talk about how it's applied in various situations. So the Reynolds number is a ratio of inertial forces versus viscous forces. So the inertial forces are related to the parameters of the flight. So we're looking at the density of the air, the velocity of the aircraft, and the length of the chord. So this would be the distance between the leading edge and the trailing edge of the wing shape. And then the viscous forces are going to be represented with this coefficient here. This is a mu, and its measure, we can talk about it, but it's a property of the air, the gases that the airplane is moving through. And we get this Reynolds number, and we can use this to understand what formulas we would need to apply, or if we need to consider the viscous forces of the air or not as compared to the flight of the aircraft. So the Reynolds number, since it's a force divided by a force, is not going to have a unit. The density of the air is going to be in kilograms over cubic meters. The velocity of the aircraft has to be in meters per second, so if it's given to you in miles per hour or knots, then or kilometers per hour, you have to convert it to meters per second. And then the length of fluid travel is the chord length of the wing shape. And the fluid viscosity, the units are going to be Newton seconds, and that's going to be divided by the meters square, the area. Okay, so that's the unit here for mu. So again, the ratio is what's happening due to the flight and what's happening due to the air it's flying through. We're not going to use these other two, so we're going to focus on this equation. So high values, this is from NASA. I got it from this NASA webpage. We'll go look at some other things in just a moment. But anything that has a Reynolds number over 10 million, you will see some very large numbers with this. We can basically ignore the viscous forces involved, and if we can ignore the viscous forces, then we can model the flight of the aircraft using the Euler equations, and these are the Euler equations on the NASA website. This is beyond the scope of this course, so I just want you to know those are there. Then if we have low values and they show that if it's less than 100, around 100-ish, then we have to consider the viscous forces. What we saw in the video, they would recommend looking at anything that's 1,000 or less. You're going to start seeing an interaction between the forces incurred from flight versus the forces that come from the fluid it's moving through. So I would just want to show you a couple of things on this simulation. Right here in the simulation, that's the Reynolds number. And then if we look at the speed, if I change the speed, you'll notice that as we increase speed, the Reynolds number also increases. So we have a direct relationship there. If we increase the altitude, you'll notice that the Reynolds number decreases. So they're inversely related. So if we decrease the altitude, the Reynolds number increases. If we increase the altitude, the Reynolds number decreases. This is because the density of the air is getting lower let's do this. The density of the air gets lower the higher we go. And then down here we have this viscosity measurement here. This is mu in our equation, and you can see that this number, as we climb, it gets lower, and as we decrease the altitude, it gets higher. So it's this relationship of density and viscosity that cause the Reynolds number to change. Another thing we could look at is if we look at the shape, let's see. Notice that the Reynolds number doesn't care about any camber shape, and it doesn't care about the angle of attack. The Reynolds number stays the same. It's a property of the length of the wing and the flight parameters more than the shape of the airfoil. Another thing we can look at is if we look at the wingspan, we can change the wingspan to anything we want, and the Reynolds number doesn't change. However, if we change the chord length, we'll see that the length increases as we or the length change. As we change the length, the Reynolds number also changes. So let's see, if we decrease length, the Reynolds number goes down. If we increase length, the Reynolds number goes up. So you can see that this simulation follows the Reynolds equation. All right. The example they give in the slide deck that you guys took notes on is this one. I'll let you read it. So, but basically it gives you a speed, an altitude, a viscosity coefficient in Newton seconds over meters squared, and a cross-section length of 1.1 meters. So we need to find the components to calculate the Reynolds number, which is R with a sub E. All right. What you would have to do in this problem is start with the altitude to find the temperature, and then use that temperature to find the pressure, and then use the pressure and the temperature together to find the density of the air. So you would have to do those calculations first before you could begin. I'm not going to ask you to do that. I'll just give you the density to start with. Also, it gives you a velocity in kilometers per hour, so you would need to convert that to meters per second. I'm just going to give you the meters per second. I don't really want to make a big deal out of dimensional conversions. So what I want you to focus on is this equation and the calculation of the solution. So again, what I would expect to see in your notebook is going to be the guess method. So it would look like this. You would have your givens, which would be the rho, and then your velocity in meters per second, your length in meters, and your mu, the value for your viscosity coefficient in Newton seconds per meter squared. The Reynolds number is what we're looking for. There's no unit with that because it's a force divided by a force. And here is our equation, rho VL divided by mu. And then show me what you put in your calculator. So this is the substitution step. And your Reynolds number would be 12,408,000. So these numbers are going to be very large. You can put everything in up to the decimal. I do have about a 4% error window. So if you put in like the first four significant figures, in this case it would be these first four numbers, then the rest could be zeros. You do have to have the right number of places because there's a big difference between 1,200 and 12 million. All right, so again, don't be alarmed with large numbers. You'll see hundreds of thousands and millions in these calculations. All right, that's a good run through for this right now. Thank you for watching.